Hello, everyone, and welcome to part 2 of extreme values of functions in calculus. So today, all we're going to do is graph. There are 6 problems, and we're going to graph all of them. So if you look at this and say, I think I got this, then you definitely don't want to watch this whole video. You want to skip ahead and see if you got all your answers correct. But I'm going to do all 6 out so that by the end you feel like you have a really great idea on how to graph. We're going to use our pre-calculus and our algebra skills. We're going to use the first derivative, and we're going to use the second derivative. And this page that I'm showing you, I won't read out loud, gives you a synopsis of how you can use, a summary of how you can use all these different things to make a graph. Number 1, the first derivative is y prime is 3x squared minus 6x. Whenever I have the first derivative, I'm going to make my first derivative sign chart and make sure you label it. So I can factor this to be 3x times x minus 2, which means the first derivative is going to be equal to 0 when x is 0, and the first derivative is going to be equal to 0 when x is 2. Now, if something's not 0, it's either got to be positive or negative. So I can quick test points. If I put in a 5, we get positive, positive. If I put in a 1, I get positive, negative. And if I put in a negative 3, I get negative, negative, which makes a positive. So now I know that my graph is going to go up because it has a positive slope, and then at 0, it's going to have a slope of 0. And then it's going to have a negative slope because y prime is the derivative, which tells us slope. And then at x is equal to 2, I know that it's going to have a 0 slope again, and then it's going to have a positive slope. Now, of course, I already knew it was cubic, so I already kind of knew that. And for that matter, now I know where it's going to be increasing, so I can say it's going to be increasing from negative infinity to 0 and from 2 to infinity. It's going to be decreasing from 0 to 2. And I can already pretty much tell you concave up and concave down. I can see that it's going to be concave down, and then it's going to be concave up. But how do I get that point of inflection? By doing the second derivative. So the second derivative is going to be 6x minus 6, which again, if I factor, 6 times x minus 1. So now I'm going to make my second derivative sign chart. And the only number to go on that is the 1. The second derivative is equal to 0 when x is 1. When something's not equal to 0, it's either positive or negative. So if you pick a number greater than 1, you'll get a positive value for y double prime. And if you pick a number less than 1, oops, I wrote 0 there, I'm so sorry. And if you pick a number less than 1, like 0, you'll get a negative number for your second derivative, which tells you that it's going to be concave down, and then it's going to be concave up, which we knew because we know the cubic shape. So your pre-calculus, the more you know about pre-calculus, the more you can predict all these answers. So it's going to be concave up from 1 to infinity, and concave down from negative infinity until 1. Now, this is a place where people go wrong. You really want just the y value. Don't tell me the point. The absolute maximum is, that means how high does the graph reach? I know it happens at x is equal to 0, but I want the y value. So whenever you want a y value, use the y equation. So when x is 0, I plug a 0 into the y equation and I get 4. So the absolute maximum is going to be 4. Ooh, absolute maximum. This actually keeps going up forever, doesn't it? So it doesn't have an absolute maximum. It's a little premature there. None. Or you can write none. Doesn't matter to me. And again, absolute minimum, none. This graph keeps going down forever. But the local minimum is going to be, maximum is going to be 4. And the local minimum, if I plug a 2 into this equation, then I get 2 cubed is 8 Plus 4 is 12. 12 minus 12 is 0. So 0. So this graph is going to go up to 0, 4, 2, 0. So it's going to look something like this. Okay? So normally, in the past, we've done this problem using pre-calc. We've said, well, we know the general shape, we know the y-intercept, and we would have found the zeros. But you're only going to be able to find the zeros if this is factorable, and it's not factorable. So the derivative gives us a whole new way to make a graph. It allows us to use the maximum and the minimum points instead of the zeros. And finally, the point of inflection is we already decided that it changes from concave down to concave up at 1. It does say point, so make sure you get the point. And when you plug a 1 in to the y equation, remember, if you want to know y, use the y equation, not the second derivative equation. So you plug a 1 into that equation, and you get 2. All right, so that's the first one of 6 problems that we're going to do today. So if you got the hang of that and that made a lot of sense to you, then you might want to try some of these on your own. Number 2. So the first derivative, I personally, in order to do this derivative, am going to change the original to 5 times 2x minus 4 to the negative 1. My first derivative is going to be negative 5, 2x minus 4 to the negative 2 times the derivative of the inside. That gives me negative 10 over 2x minus 4 squared. Remember that there are 2 things that make a critical point: where the derivative is equal to 0 and where the derivative does not exist, which we did not discuss in this one because the derivative always exists. There's no cuffs or corners or asymptotes, no points of discontinuity, nothing that would make the derivative not exist. But on this one, we have an asymptote at x is equal to 2. So you've got to still use your pre-calc. You can't just make your pre-calc go away. And I know it has a horizontal asymptote at 0. So honestly, if it was just asking you to make the graph, you probably could make the graph right now just by plotting 2 points. One of them can be the y-intercept. If x is 0, then negative 1 1/4. Now that I see the negative 1 1/4, I think to myself, I already know what this graph looks like. I make a table. I pick a number greater than 2 to make sure I get one of these 2 branches. So I pick 3. And that gives me 5 over 2, which is 2.5. So 3, 2.5. Oops. The asymptote is down there. So the question just said graph. You totally don't need calculus. This is super important that you know this. It also means that without doing the calculus, I can already tell you about concavity. It is definitely concave down from negative infinity until 2, until I reach that asymptote. And it's definitely concave up from 2 to infinity. There's no absolute maximum, and there's no absolute minimum. It goes up forever, and it goes down forever. Now, one thing that a lot of people get wrong is the local max and the local min. They always think that it's somewhere right here. I'm not really sure why, but it's very common. But if you think about it, a local minimum means that there's no points nearby that are lower. Well, right there, there's a point that's lower. So be careful. If this has an asymptote like this, then there is no local maximum or no local minimum. It's not like the kind of graph where there's an asymptote where it comes up and it actually reaches a height of some kind. If it just goes down like this, then it doesn't have a local max or a local min. Okay, point of inflection. So it does change from concave down to concave up, but there's no point. That's the key word. There's no actual point. There's an asymptote where it changes concavity, but is there a point of inflection? That means where it actually changes. And where is this function increasing? And where is it decreasing? It's decreasing here, right? All the slopes are negative. So it's decreasing there. And then you start over again, and it's still decreasing. It's always decreasing. So it's decreasing from negative infinity until 2. And then at 2, it takes a little break. And from 2 to infinity. And it's never increasing. So look at this. I literally did this entire problem with pre-calculus. I have not done the calculus. The only thing that is forcing you to do the calculus is the fact that I actually asked for the first and second derivative. But what I'm going to do now is show you how those answers still make sense. So on the first derivative, this is never going to be equal to 0, but there is a critical point at 2. So now I do my first derivative test. But think about this. No matter what number I plug in on either side, it's definitely going to be negative on the top and positive on the bottom because it's going to be squared. So a negative over a positive makes a negative. And no matter what I pick over here, once you square that denominator, a negative divided by a positive is a negative. So since this is my y prime, this tells me about the slopes. This tells me the slopes are always negative. Does that match what I thought? Absolutely. The slopes are definitely always negative. So the first derivative is y prime is equal to negative 10 over 2x minus 4 squared. And the second derivative. So y double prime, I'm going to start with this one because it's in a really good form for it. Actually, I'm going to change it to y prime is equal, I'm just going to move that 2. Negative 10 times 2x minus 4 to the negative 2, but meaning I'm going to leave it with my negative exponent. So y double prime is 20 times 2x minus 4 to the negative 3. So y double prime is 20 over 2x minus 4 cubed. But since I have a narrow line, I'm going to leave it as 20 times 2x minus 4 cubed. So where can points of inflection occur? Points of inflection can occur where the second derivative is equal to 0, which it's not ever going to be equal to 0, because only the numerator can make something equal to 0. Or where the denominator would be equal to 0, which means it does not exist. So again, a 2, just like before, would make that denominator 0. So 2 is one of my critical points. If I plug in a number bigger than 2, let's say 5, I get 10 minus 4 is 6. Well, 20 over 6 cubed is definitely positive. Notice you don't have to find the actual number. You just need to understand if it's positive or negative. But if I plug in a number like 0, I'll get negative 4 cubed, which is going to be negative. So a positive divided by a negative is a negative. And remember, what does second derivative tell us? Second derivative tells us where something is concave down, and where something is concave up, right there. And at 2, I don't actually have a point of inflection, but that's where it changed concavity, so it is a critical point. All right, let's do number 3. So again, let's do as much of this as we can using pre-calculus. I personally am going to change this to x plus 1, x minus 1, because then I can see my two vertical asymptotes are at negative 1 and positive 1. My horizontal asymptote, since my powers are the same, I do 1 over 1, which is 1. So you already know a lot about this graph. If you're really, really great at your math, you'll also know that this function is even. Because when you have an x, it doesn't matter if it's positive or negative because it's going to get squared in both cases. Remember, you can't just look at a square and say something's even. If this had been x squared over x squared plus x minus 1, it would not have been even because this x would have meant that a plus 3 would give you a different answer than a minus 3. But without that there, a plus 3 and a minus 3 are going to give you the exact same answer. So if the graph is even, then that rules out this concept. It has to either be this to be even or this to be even. So this is great. I already know so much about this graph from pre-calculus. Calculus is not even important yet. So how can I find that? Well, let's plug in 0 and find the y-intercept. Notice that's not one of the choices here. It would have been if you were in pre-calculus. It was when you were in pre-calculus. So 0, 0. So right there. So I'm guessing that this is the function. I'm going to make a quick table. I'm going to plug in 2. When I plug in 2, I get 4 over 3. Is that what I expected? You bet it is. 1 1/3. I totally expected to come out there. And negative 2 should be the same because it's even. Now, if all you had to do is make the graph, you would be done, and pre-calculus would have gotten you it. But we want to know calculus questions. So without even doing the calculus, though, where is the function increasing? From negative infinity up until negative 1, and from negative 1 up until 0. This one's a little tricky. Do you follow that? It's increasing, 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 and it stops. So I have to stop at negative 1. And then when you start off again, though, what is it doing? It's increasing again. A little tricky there. Where is it decreasing? At 0, it starts to go down. And it goes down until x is negative 1. But then it takes a break. So you do have to break. You can't just sit there and say, oh, it's decreasing from 0 to infinity, because it's not. It takes a break. And then from 0 to positive 1, and then from 1 to infinity. Where is it concave up? It's concave up in these two sections. So it's concave up from negative infinity to negative 1, and again from 1 to infinity. Where is it concave down? Just in this little section. So from negative 1 to 1, which is not an ordered pair. That represents an interval. Absolute max, there's none. Absolute minimum, none. Local maximum, there is one, 0, 0. Local minimum, there's none. So this graph is going to go down, and this point is not a minimum. Like I said, I don't know why people say it, but it happens all the time. The graph keeps going down until it reaches that asymptote, and then it kind of follows the asymptote, but there's no local minimum. Now, the graph does change inflection. It goes from concave up to concave down, but that happens at asymptotes. So there's no actual point of inflection. So if you're good at your pre-calc, you could literally do most of these problems with just pre-calculus. So first derivative. So the first derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. That gives me 2x cubed minus 2x minus 2x cubed over x squared minus 1 squared, which is negative 2x over x squared minus 1 squared. Y prime is equal to 2x over x squared minus 1 squared. If you didn't know how to do this using pre-calculus, then you would make a sign chart and on it you would put where the derivative is equal to 0, which when x is 0, that would cause it to be equal to 0, and where the derivative does not exist. So it does not exist at 1 or -1, because that would give you a 0 in your denominator. And then I would plug things in. But this is not hard, because look, the bottom is squared. So no matter what you put on the bottom is going to be positive. So really, you just have to look at the top. If I put in a number like 8, I get a negative on top. If I put in a number like 1/2, I still get a negative on top. If I put a number in like -1/2, though, I get a positive on top. And if I put a number in like -8, I get a positive on top. Okay, finally we got one. Positive, positive, negative, negative. It did not alternate. Positive, negative, positive, negative. So if you're not good at your pre-calc and you had done it by calculus, this is what you would have gotten. And you would have had to look at this and say, hold on, it's rising, but then it takes a break and rises again. Look at that. It rises, and then it takes a break, and it rises again. And then it falls, takes a break at 1, and then it falls again. You have to admit, it's very cool. So it completely confirmed the answers that I got using pre-calculus. Okay, so unfortunately, it does ask for the second derivative, so you are going to have to find that. So this second derivative is pretty terrible, right? I have to start with that. So I have to do the bottom, x squared minus 1 squared, times the derivative of the top, minus the top, negative 2x, times the derivative of the bottom, which is 2, times x squared minus 1 to the first, times 2x, all over x squared minus 1 squared. So if I factor out a negative 2, and I factor out an x squared minus 1, we've talked about doing this before, now it's going to come in really handy, and I actually can factor out, no, that's it. So from this one, I took out the negative 2, and I took out one of these, so I'm left with 1 x squared minus 1. And here, I took out the negative 2 and this, so I'm left with 4x squared, which is negative, over x squared minus 1 squared. This cancels with one of these, and I'm left with negative 2 times negative 3x squared minus 1 over x squared minus 1. Did I get that right? I think so. All right. It's ugly. Oh, I know why that's not right. Because this is to the fourth. This is the fourth, so that brings it down to the third. All right. I was going to say that didn't look exactly right. So, or you can write it as 6x squared plus 2 over x squared minus 1 cubed. Okay, so did you see the mistake there? The bottom was already squared, so I missed that it's the bottom squared. So squared squared would make it to the fourth power. I'm just going to write C below. I am going to put this in big letters and hope people see it as they scroll through. You're probably going to want to watch this one. It's filled with some really interesting information. The first of which is that I have a great shortcut for you for this derivative. You think about this derivative. You thought the last one was ugly? Well, this one's going to have the quotient rule and then the quotient rule again. So as much as you're not going to like it, the shortcut for doing something like this is going to be using long division first. So watch this. You remember synthetic? You take the opposite of this number, and then we're going to put the 1, 1, negative 2 here. 1, 1, negative 2. So add, multiply, add, multiply, add. And I can rewrite this instead of as an improper fraction, improper meaning the top is higher than the bottom. I'm going to change it to a mixed number, x plus 3, I got that from here, and then my remainder, plus 4 over whatever I was dividing by, x minus 2. So this one would be, it goes in 3 whole times, and then the remainder would be 3 over the 4. This is an improper fraction. We've changed it to a mixed number, which in derivatives is going to be super important because watch this. If I move that x minus 2 to the bottom, or sorry, to the top, I can take the derivative so fast. You ready for this? Y prime is equal to the derivative of x is 1, the derivative of 3 is 0, minus 4 times x minus 2 to the negative 2. Beautiful. Y double prime, even more beautiful. The derivative of 1 is 0, and then when I bring that down, I just get 8 times x minus 2 to the negative 3. You have to admit, knowing that you're about to do quotient rule and then quotient rule on top of the ugly answer, this is totally worth the minute that it takes you to do the synthetic division. So the other reason to do the synthetic division and change it to a mixed number is because now you also have the asymptote. Do you remember that the oblique asymptote is the non-remainder portion? The oblique asymptote is the non-remainder portion of the answer. So y is equal to x plus 3. Now we know that that's the asymptote. It's going to help us make a graph. The vertical asymptote is at 2. Okay. So I also want to take, the other reason I said watch this is I want to take a little break and explain why the asymptote is just the x plus 3. For years, I've told you to just ignore the remainder, but I'm finally going to tell you why now that you're in calculus. And that's because now you've learned limits. The limit as x approaches infinity of x plus 3 over 4 over x minus 2. When you approach infinity, 4 divided by infinity, 4 divided by something infinitely huge, pretty much becomes 0. And you'll just get x plus 3. Whatever number x is. So that's why we always discounted the remainder. It's not part of the oblique asymptote. Because remember, the oblique asymptote only tells you the end behavior. It doesn't tell you what happens right here. But in the end, it's going to follow it on one side or the other. So there's an explanation that I didn't give you last year. Where is the function increasing or decreasing? So probably it's increasing until something and then decreasing, or maybe it's increasing the whole way. How can we find that out? You can use your pre-calculus. For these last 3, I'm going to do the calculus first to make sure that that's a method that makes sense to you. So I take my first derivative and I set it equal to 0. So I can make my sign chart. X minus 2 squared is equal to 0. I'm going to make that 1 is equal to 4 over x minus 2 squared. I'm going to clear the fraction, x minus 2 squared on both sides. Now I have x minus 2 squared is equal to 4. X minus 2 is equal to plus or minus 2. I took the square root of both sides. And therefore my two answers are, if I add 2 to the 2, I get 4. If I add 2 to the negative 2, I get 0. So there's always 2 things that you put on your y prime chart. First of all, don't forget to label it y prime. There's going to be a y double prime chart. So on my y prime chart, I want to put down where the derivative is equal to 0, but don't forget also where the derivative does not exist. And this derivative does not exist when x is equal to 2. That's going to give you a 0 in the denominator. So I do have to check all these different spots. I would say of all the problems we're going to do this year, this is the hardest one to plug in onto the sign chart. So if I pick a number like 5, I get 1 minus 4 over 5 minus 2 squared. This is not intuitively obvious whether or not it's positive or negative. So I usually simplify it just enough And then I can see, oh, 1 is bigger than 4 nines, so it's going to come out to positive. I still don't finish it, but at least I can do that much. For the next one, 1 minus 4 over 3 minus 2 squared. So I'm plugging in a 3, which would be 1 minus 4 over 1, which would be negative. For the next section, 1 over 4 minus 1 minus 2 squared. On the bottom, I get a 1. So 1 minus 4 is negative 3, which is still negative. Well, another problem that didn't go positive, negative, positive, negative. I told you it was going to happen. Got to watch out. And 1 minus 4 over, let's pick a big number, negative 5 minus 2 squared. So again, this, I don't actually know what it is, but I know it's 4 over 49. Is that bigger than 1? It's not. So this is going to be positive. So now I know the graph rises and then falls, and then falls and then rises. Well, now I definitely know it falls, it rises, falls, falls, rises. I can totally picture it. And I know that its maximum is at 0, which is not a bad number to plug in. 0 is actually going to reach 1. So its maximum is going to be there. Its minimum, this happens because of the asymptote, and its minimum is going to be at 4 comma something. Now I want to know the y value. Which equation do I use? The y equation. The y value, use the y equation. So when I plug 4 back into this equation, I get 3. So 1, 2, 3, oh, sorry, not 3. Terrible math there. 9. 9. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that problem way up there is 4, 9. Something like that. Can't even see it. So the absolute maximum, there's none. And the absolute minimum, none. But the local maximum, okay, this is really funny. The local maximum is 0, and the local minimum is 9. And sometimes that throws people. They're like, how could the maximum be a smaller number than the minimum? Because it's local. It just means compared to everything around it. So you could just graph it, and that would be fine. I do want to point out really quickly that if you were trying to get to college and you have to make a really good graph, you could go back and use your pre-calc skills. This is x plus 2 times x minus 1 over x minus 2, which means the x-intercepts are at negative 2 and 1. Oh, we actually came really close just by making a sketch. So negative 2 and 1. But you didn't actually need that to answer the rest of the questions, which are, where is it increasing? From negative infinity to 0. Union 4 to infinity. Where is it decreasing? From 0 to 2. Union 2 to 4. Now, concave up and concave down are supposed to be second derivative, which I can do. Y double prime is equal to 8 over x minus 2 cubed, which means I make my sign chart and I put two things on it. Where the derivative is equal to 0, which the second derivative is never going to be equal to 0, or where it does not exist, which is 2. I plug in a number bigger than 2, like 4, and I cube it, I'm going to get a positive answer. But if I plug in a number like 0, negative 2, and cube it, I'm going to get a negative answer. But I already knew that. Look, concave down and concave up. I didn't need to do the second derivative sign chart, but I'm just trying to show you that it does work. So the function is concave up from 2 to infinity, and concave down from negative infinity to 2. There is no point of inflection. It does change inflection at the asymptote, but it's not an actual point. All right, we still have 2 more, so I hope that you're getting the hang of it. I am going to do one more with the oblique, so we can do the long division. So this one doesn't have just x plus or minus a number, so I'm not going to use synthetic. There is a way to use synthetic if you can figure it out, but just to show one with long division, x squared plus 0x, don't forget your 0x to hold that place, which you would have had to done in synthetic also, So we need to get an x squared. So x squared divided by 2x is going to be x over 2, which is 1/2 x. So that's what you want. You want 1/2 x. If you're ever not sure how to get what you want, just do the first thing divided by the first thing, and that'll always tell you what it is in long division. So 1/2 x times 2x is x squared. 1/2 x times 4 is negative 2x. I change my color so I can change the sign. And I get 2x, bring down the 3. And then, again, if you're ever confused about what goes here, do the first thing divided by the first thing. And 2x divided by 2x is 1. 1 times negative 4 is negative 4. 1 times 2x is 2x. I change my color so that I can remember to change the sign. And I get 1. This fraction, which would be hard to do as a first derivative and second derivative, is equivalent to 1/2 x plus 1 plus 1 over 2x minus 4, which I'm going to rewrite as 1/2 x plus 1 plus 2x minus 4 to the negative 1. Its first derivative is going to be 1/2 minus 2x minus 4 to the negative 2 times 2. Its second derivative is going to be the 1/2 goes to 0, and let's just pretend that 2's out in front, would be positive 4, 2x minus 4 to the negative 3, but still times the derivative of the inside. Of course, both of those can be simplified. I'll put them over here. Y prime is 1/2 minus 2 over 2x minus 4 squared, and y double prime is 8 over 2x minus 4 cubed. Now, I'm going to do it in a different order this time. Sometimes it's nice to have the second derivative first. So the only thing I can put on this is where the second derivative is equal to 0 on the bottom, which is at 2, which I'm sure you knew right away. There's an asymptote at 2. Let's go ahead and draw that asymptote at 2. And so if I plug in a number bigger than 2, like 10, then 20 minus 4 is positive. If I plug in a number like 0, I'll get negative 4 cubed, which is negative. So now I know that this is going to be concave down and then concave up. So it's going to look like our last one did. I can use my long division to give me, remember, just this part, not the remainder, just this part gives me my oblique asymptote. So I go up to 1 and then up 1 over 2, up 1 over 2. This is all of your pre-calculus and your calculus coming together. That's why I always tell kids, if you don't take calculus, you won't see how it all fits together. We could even do Y-intercept to bring in a little pre-calc. If x is equal to 0, then I get 3/4, which is positive, which confirms that I'm going to be working in this region, and that is going to be concave down. So I can already fill in concave up from the asymptote to infinity and concave down from negative infinity to the asymptote. I can already confirm that there's no absolute max or min. There's no point of inflection. But I do need to get the maximum by taking the first derivative and setting it equal to 0. So 1/2 minus 2 over 2x minus 4 squared. I will say this gives people a lot of trouble solving this equation, this algebra. So I'm going to move, I'll move the other one. I'm going to move the 2 over 2x minus 4 to the other side. I'm going to multiply both sides by the 2 to clear that, and by the 2x minus 4 squared to clear this. This gives me 2x minus 4 squared is equal to 4. I take the square root of both sides, and I get 2x minus 4 is equal to plus or minus 2. So if it helps you, you can do it separately. You don't have to be a hero. 2x minus 4 is equal to negative 2. So 2x is equal to 6, x is equal to 3, or 2x is equal to 2, x is equal to 1. Those are the two places where the first derivative is equal to 0, but don't forget, there's another thing, and that is 2. Okay, do you remember last time we said how hard it was to plug numbers in to this derivative? So hard. This is where knowing your pre-calc pays off. I would sit there and say, look, it is definitely going to rise and then fall and then fall and then rise, because I know what it looks like. And I know it's going to rise until x is equal to 1. I still need to actually find that value. So keep in mind, if I'm trying to find a y value, I need to use the y equation. So when I plug a 1 into my equation, I get 1. So 1, 1 is where it goes to, which makes sense with my y-intercept. It's rising until 1, and then it's falling. At 2, that's just an asymptote. And 3, I want to know the y value. I use the y equation. And when you plug in 3, you actually get 3 again. 1, 2, 3, 1, 2, 3, which also fits with how I thought the graph was going to look. So it is increasing from negative infinity to 1, and then again from 3 to infinity. It is decreasing from 1 to 2, and again from 2 to 3. Okay, we have just one more to do today. This one, cut us a little break if you want to try it on your own. This one is already in long division, like I've already done the long division for you. So I am going to just do one minor change, x to the negative 1, before I do the first derivative. The first derivative is 1 minus x to the negative 2, and the second derivative is positive 2x to the negative 3. Looking at the second derivative, where that's equal to 0, it's never equal to 0. But 0 is still on my second derivative sign chart because two things go on the sign chart: where the derivative is equal to 0 and where the derivative does not exist. If x is a positive number, the second derivative will come out positive. And if x is a negative number, the second derivative will come out negative. So now I know my graph is concave down and then concave up. Using a little bit of pre-calc, I do know that it has a asymptote at 0. X is equal to 0. Oop. Right there. And it has an oblique. Do you know where it is? This one's a little tricky because I've already done the long division. So remember that the purpose of the oblique asymptote is to tell you the end behavior. The end behavior. So it's the limit as x goes to infinity. Well, as you go to infinity, what's going to happen to this guy? As you go to infinity, this is going to equal 0. So only this is my oblique. So y is equal to x. And in the other direction, y is equal to x. So now I have my oblique asymptote. And I know it's concave down and concave up, just like the last two. So I need to find that max and that min. Or should we go ahead and fill some other stuff in? There's not going to be a point of inflection. There's not going to be an absolute max or min. It's going to be concave up from 0 to infinity and concave down from negative infinity to 0. But I need the first derivative for all the rest of these. These all go together. So the first derivative is 1 minus x to the negative 2. I set it equal to 0, and I simultaneously Move that to the bottom. I'm going to rewrite it like this. I'm going to clear my fraction. I get 1 is equal to x squared. X is equal to plus or minus 1. But what else needs to go on your sign chart? Oops, just first prime. Where the derivative is equal to 0, but also where the derivative does not exist. So x can't be 0. So two things always go in your chart: where the derivative is equal to 0 and where the derivative does not exist. Again, do I have to try and plug numbers in here? Not really. I mean, I can. If I pick a number like 5, 1 minus 1 over 5 squared is definitely positive. But you also knew that just from this concept that it's falling and then rising, falling and then rising. And on this side, it's rising and then falling, rising and then falling. So there's no one way to do these. There's an understanding of what's happening. So again, I need to know the y coordinate. So I use the y equation. When I plug in a 1, I get, sorry, a negative 1, I get negative 2. And when I plug in a positive 1 into the y equation, I get positive 2. So negative 1, negative 2, positive 1, positive 2. This graph looks like this. All right, I hope that you understood this. I know there's a lot to learn. You guys are doing such a great job. Oh, I'm sorry. I just realized I didn't actually write this down. Increasing from negative infinity to negative 1 and from 1 to infinity, decreasing on negative 1 to 0, union 0 to 1. Its max, as weird as it is, its maximum is negative 2. And its minimum is positive 2. I just have to go back. Did I finish that? Oh, look at that. See, I didn't finish that on this one either. And the local maximum on this one, what was the y value we got there? At 1, it was 1. That was the maximum. It's the highest of everything around it. And the minimum was 3, which is the lowest of everything around it. Okay. All right, you guys. This was the end of extreme value B. There's one more that will do the last few problems. You have a great day.